Hello there, this is our video on 184N powerhouses. They were black oil fired boilers. There are 3 boilers in the powerhouse. They burn black oil, bunker C, number 6 fuel oil, a bunch of different names for it. It's a real thick oil, has water, sediment in it. It's kind of a dirty bottom end of the oil refining process. I believe nowadays they're cracking it, reclaiming it. Burning black oil, I believe after 2015 wasn't allowed. But this is another piece of history. 100N use the boilers, provide steam for startup and for shutdown. Was really the main use for them. There are 3 boilers. Had a Foster Wheeler boiler, put about 575,000 pounds an hour. Then there are 2 combustion engineer boilers. They put about 200,000 pounds an hour. They burn black oil, use diesel for igniters to start the black oil. It came in by truck mostly. You could also bring them by rail car. They added different oil conditioners, Nelco 158, 158D, and 8258. These did various things for the fuel oil. It came in, usually was pumped off. Transfer pump, it went back to the tank. It had to be at least 118 degrees coming in or it wouldn't pump. You have to keep this well hot or you can't pump it. This tank usually ran about 118, 120 or so. Had steam heat coils in the bottom. Held a little over 1 million gallons of black oil. There's a lot of heaters involved to keep this oil hot and moving. The pumps were a gear pump. To pump it, had a lot of strainers in it. It's pretty dirty oil. From the number 6 fuel oil tank, we'd fill the day tanks for the powerhouse. They hold about 35,000 gallons apiece. They had steam heat. They'd run about 130 degrees, trying to keep the oil warm. From there, it went through a strainer, gear pump, and then a heater. Anytime you work with these systems, make sure you get the vents and drains in before you put oil on it. Just a word of advice. It can make a hell of a mess. A drop of this stuff will cover probably an acre, it seems like. It's real sticky and it spreads everywhere. Now the heater, I believe it ran around 200 degrees, a little over 200 degrees in the oil temperature. The oil temperature is critical for getting it to atomize right. From there it went to the burners. You had the igniter would start first. This used air, diesel and air, and then it's an igniter air fan that create the flame. The scanners had to see the igniter flame for let the fuel valves open. Flame scanners, they look for ultraviolet. You can't look for infrared because the whole boiler is full of infrared, so there you always ran off ultraviolet. You had your main gun block valve, and then you used steam for the atomizing media. Also had air registers around each burner. Then there's a valve between the steam and the main gun to blow it out. So when it shut down, the oil valve would start closing, igniter would come on. Then both steam valves would open to blow out any black oil out of the guns. To start the guns, you had to push them in manually and then valve them in. So usually the boiler is kept warm with steam. During reactor scram, you'd have to go push in the main guns, valve them in, then they'd start them one at a time. Had about a half hour to get the boiler up to full load and carry the steam load. There's enough thermal energy left. Now the Foster Wheeler boiler had a firebox, had 8 burners, 2 decks of them, 4 burners on a deck. Here's the firebox. Flue gas went up here, down and back on typical boiler. If you ever had a high stack temperature, you may have problems in here with the baffle may have got damaged or holes in it. Ash accumulated here, had soot blowers on it. These weren't really ran a lot, so you didn't have to worry too much about soot. I had an FD fan that fed the air into the register, so this was a forced draft boiler. Positive air pressure in here. Blew it through and went out the stack. Stack provided a little bit of draft. They ran about 450 PSI. Big thing with black oil, heavy oil fired burners, oil temperature is critical. Too cold oil does not atomize. too hot, vaporizes, cokes up. So your oil temperature was fairly critical. Steam pressure, if you had too high a steam, it'd back out the oil, the way it went down the gun. And too low, you wouldn't get the atomization, so you'd have a lot of smoke and not good burning, plus oil could drop down the bottom of the boiler. Oil pressure, too low does not atomize. You get too high, you have atomizing problems. So these things really come into play: oil pressure, steam pressure, and oil temperature to get a good burn. Plus you had to have the correct amount of air for the fuel. I know you always want to keep the air over the fuel gauge. If you didn't run your air right, they would smoke quite a bit. But when they were set right and running good, there wasn't much smoke come out. They worked pretty good. There's also the diesel tanks. You had 400,000 gallon diesel tanks, number 2 diesel. These provided fuel for the igniters, and the main use was to fill the 182N day tanks for the high lift diesel pumps, the fog spray diesel pumps, low lift diesel pumps, and fire pumps. These were set up to gravity feed, so the plant could be evacuated and your emergency cooling pumps would run for quite a long time, at least 10 days, but it's probably a lot more than that. So basically this was the black oil fired boilers in 184N. There are 3 boilers. They burn black oil. One thing about black oil has a really high heating value per gallon. But at room temperature, it's fairly thick and you really can't pump it, so you have to keep it warm. As far as I know, these really aren't used much anymore. I know ships probably have them still. This is really big in marine industry. Here's a little section on starting up one of these boilers. First you had to purge the boiler, run the FT fans, air registers had to be open. I believe this is a 5-minute purge. It'd blow out any combustible gases out of the boiler. For cold startup, you'd have to run the igniters. You'd put all the igniters in because you had to have steam for your main guns to atomize. So I'd run the igniters. As soon as you had enough steam pressure, you could start heating up your fuel oil. These lines restrict back to the pump to keep these lines warm all the time. Otherwise the stuff would set up. So once you had your steam, you could start one of the guns. And usually it was an emergency startup for a scram, so you'd go in there and valve in all the guns and then you'd start them one at a time. But for normal startup, you'd start up a gun, start warming up steam lines. This was primarily used for the primary drive turbines and also the turbine generator in the plant. The plant had 2 separate electrical feeds, as we've mentioned. One was in-house power. It ran off steam off the reactor, or also it can run off steam off the boilers for startup and shutdown. So the steam from here went for providing atomizing steam, the heating steams. Mostly the turbine generator for power is about a 13 megawatt generator. And then went for the primary coolant pump drive turbines. I believe the boiler's going to run them up to about 1700 RPM. But at that point you had enough reactor steam where you could take over with the reactor steam and run the coolant pumps up to full speed. So basically startup, you had to have steam, so you'd have to run your igniters, get steam in the boiler, heat up the oil, had to have steam for atomizing. For shutting the guns down, like we mentioned, oil valve would close. Once the oil valve started closing, the igniter would start, and then it would blow down the oil gun with steam to clean out all the oil in the gun, and then also atomizing steam would work just to burn the oil in there. This just shows the igniter here, but both these had an igniter and a main gun together, and they're 2 decks of burners. There had been problems with the thing dumping oil in the boilers other places. So that's why you'd have good flame scanners. That was always a concern to fill the boilers with oil. That's happened. Not here, but other places. And so you have your 2 flame scanners. It had to see the igniter scanner, before it let the valves open as kind of a safety feature. Then when it was running, you had to have your main flame scanner. If you lost your main flame scanner, it would trip the burner off. Like we said, these looked at ultraviolet light. Fairly simple boilers to start up. It had a lot of the older control systems on it, relays, and didn't have any PLCs running it at first. But it was a simple boiler and they worked quite well. This is our video on steam jet air ejectors. 100N used steam jet air ejectors for the main turbine generator and also the feed, the reactor cooling turbines. Pulling vacuum on condensers, there's two ways you can do it. One's mechanical, using mechanical vacuum pumps. And number two is the steam jet air ejectors. Steam jet air ejectors work very well. There's no moving parts. They use steam, and the heat in the steam is recovered in the condensate. The way they work, you have a steam source. Steam comes in through a nozzle. It kind of creates a high velocity here and spreads a little bit, which creates a low pressure. And also want to mix with the gases coming in. You'll have your air coming in, maybe a little bit of moisture, but the steam comes down, it grabs the air, forces it down this part of the ejector. This increases the velocity of it as it narrows down, so you have to have higher velocity. As the velocity increases, the pressure decreases. So this creates a low pressure on this part of it here. Same volume comes through, so in order to get the same volume through, the velocity has to increase. This part of the ejector, velocity is decreasing and pressure is increasing. It's kind of like a volute on a pump. So this part, you're creating a negative pressure, low pressure pulling in. This part, you're creating a high pressure to force the gases in the low pressure area to a high pressure. From here, they went through a condenser. This used the condensate off the surface condenser. So they come down here, you condense the steam, heat the water up, reclaim all your heat energy. Condensate would come out. This went back to the surface condenser. Then your air would come out. A lot of these, you could put another ejector right here on this part of it, and then you could pull down the vacuum down to a couple inches of mercury. They were fairly efficient. We also had hoggers where you just have a steam jet air ejector, and from here it just went straight to atmosphere. That was good for pulling a lot of air quickly. If you lost vacuum, for some reason you could open that up. That's also for startup, you can move a lot of air quickly. It just vented out the stack. But steam jet air ejectors usually had two in series. You had one stage, and the second stage was the same as this. So the two stages together, it could pull a very good vacuum. The condensate was reclaimed back to the surface condenser, and any heat energy here was used to heat the condensate from the surface condenser back up. These were, say there's no mechanical parts. Mechanical air ejectors, now you have a motor and moving parts, although they use a water ring for the sealing and the actual working mechanism. So they're really fairly good too. And that's the steam jet air ejector. Nowadays, pretty much everybody's using mechanical vacuum pumps, but these are still used in some applications, and they work really quite well. The maintenance isn't much on them, and they'll run for years without any problems. Okay, here's a little thing on steam drums. This is how the steam drums in the Foster Wheeler were set up, and also the combustion engineering boilers. We got a little slideshow, some diagrams, shows this a little better. This is just kind of a rough overview of the boilers. The steam drums are really very critical for getting as dry steam. This type of drum was really very efficient and worked well. It's a natural circulation boiler. So the way they work, you have water on this side. On the risers, you have a steam water mix, which is lighter with the steam, and the water specific gravity is less, so then it'll rise up. The harder you fire this boiler, the lighter this mixture becomes, and the faster the circulation increases. That's why most of these type of boilers, 2400 psi is about it. The steam and water mixture start losing a lot of specific gravity, becomes a little more dense. At 3201, 3206, hits supercritical. At that point, steam and water have the same density, so that they'll no longer work for natural circulation, have to use forced circulation. But these at 2400, you'll still get circulation in here. Low pressure boilers worked really well because you had large steam bubbles, and they had really good circulation on it. Okay, this is the downcomer. This would be mostly water. Your feed water would come in here. You want this as cold and as dense as you can get it. This is back from the less heat part of the convection section. Your fire would be on this side. You want these tubes to pick up all the heat they can. The downcomers, you want to keep this from developing steam. Took us down to the mud drum, and then on the way back up, so you produce the steam. The water would go down, downcomer, down to the lower water ball headers or the mud drum, and as it came back up, it'd pick up the heat and it'd start forming steam bubbles. You didn't want sheets of steam forming on the tubes. That would overheat the tubes. Most of the time, there wasn't any problems. You just wanted bubbles in here. You don't want film boiling and other things from too much heat in here. It came up to the steam drum. There's a baffle in there. It kept the steam water mix separated. I went to the top part. From here, this is where the separation starts to take place. The water drops back down. The steam's supposed to separate in here. The top surface area, the steam bubbles come out of the liquid. You get a little bit of moisture in here, little droplets and stuff as the steam bubbles break, pick it up. This part here, the baffles were corrugated plates. If you change the direction of flow quickly, the gas will go through and the solid water particles will hit the plates and drop out. So this part here, you have the droplets are drained down here. You had a drain pipe went back down below the surface water. So the purpose was this part was to knock out all the water droplets in the steam. Then you had a dry box, had screens in it. Purpose of this was just to remove any more moisture. So you wanted fairly dry steam coming out. Where you can get in a problem with these, too high a drum level, you could carry water over your steam line. If you're running superheat boilers, your superheater section is going to take a beating. That's where everything's going to plate out in it. You won't know you have a problem until you start burning up tubes. You can also get a lot of foaming, which will carry water over. Used to be priming, which also be a big slug of water come out, but that's kind of the old days. With the water quality nowadays and stuff, you really don't have a problem with foaming. It's mostly drum level issues, like shutdown. If you're not paying attention, overflood the drum, you can fill the superheaters with water. If you're using a volatile chemistry, it's probably not as bad as some of the older non-volatile phosphate. You're plating out solids in the surface in the superheat, and that will cause damage eventually. From here, the water, like I said, you have your continuous blowdown. You want this line as close to the surface as you can get. This is where the concentrated solids will be. So you take a slipstream of water off to try and maintain chemistry, get rid of any dissolved solids in the water. There's also chemical injection can be added to the drums up here. Here's your feed water line comes in, there's holes, we're going to cross the whole length of the boiler. So typically this water is a little bit cooler than the drum water. So you want to add this down here so it goes down the downcomer. If your level gets too low, you'll lose your continuous blowdown. Your boiler chemistry will start losing control of the solids, conductivity. If it's too high, you can carry over. So sometimes, your drum level has a sight glass and pressure transmitters, and it's working off of specific gravity. This is cool. You have your water level here. Usually they're really close. They're almost dead on, but if you happen to get a lot of bubbles, steam bubbles, and just a little bit lighter mixture in here than here, you're going to have a slight difference. So you think your drum level's here, and actually it's a little bit higher. Some boilers, you fire really hard, there'll be quite a difference between the length of the drum across the boiler. One area gets more heat. it could be a little bit higher than the other end if you have a long steam drum. So basically their sight glass is giving you a reference of the specific gravity, and inside it could be off a little bit. That's why you got to watch outlet temperatures and different things on your boiler. But natural circulation for lower pressures work very well. And that's about it for this video.